All right, so the first thing is let's be clear about the test. So exam 2 is Monday. If you want to take it with the day class, it's Tuesday. Monday is in this room, 1326, 6 o'clock. Tuesday is in C 1016 at 3 p.m. And the topics are vectors and 2D kinematics. And so the stuff we did last time, I think it was, we just started it last time, but isn't going to be on the test. And the stuff that I'm going to talk about today isn't relevant for the test. But before I go back into that, I'd be happy to answer any questions you have about practice problems or anything, you know, related to the test. Anybody have anything? Okay. And I'd be happy to answer questions during lab tonight too. So back to kinetics of particles. Where we are so far with this is we have talked about the most important equation in this class. And that is Newton's second law. And Newton's second law says the force, the net force vector is equal to the mass times the acceleration. But that, and I said that that equation doesn't do you any good unless you know what forces you're talking about, you know. You can't just pick out what forces you want to look at, pick out what object's mass you want to talk about, pick out what acceleration, what object's acceleration you want. These have to have a defined relationship. And so this F net is the sum of all forces on the chosen object. And the mass is the mass of the chosen object. And the acceleration is the acceleration of the chosen object. And I also said that you can't use this equation if you don't have a certain type of coordinate system. This only holds in inertial coordinate systems. Anyone, without looking, remember what the requirements are for an inertial coordinate system? Yep, not rotating. It can be moving, but it can't be accelerating. So some kinds of motion are okay, but just no acceleration. A coordinate system that's moving with a constant velocity actually is okay. You can use this equation and everything comes out fine. it's when the origin is accelerating, there's a problem, or when it's rotating. Those are the two things that mess up your answers and makes for cool music videos. But they had to edit out the part where in that music video, you didn't see the end where they were trying to use Newton's second law and it wasn't working. Like you only saw like the glamorous part. But at the end, I don't know. That didn't really happen. And the last part of this sort of summary is, so this F net, that seems like a lot to take into account. But it turns out that all of the forces that we have to deal with fall into two categories that are sort of easy to evaluate. So all the forces this semester, by the way, there'd be a few more in other areas of physics if you talk about electric fields and magnetic fields, but still it doesn't make it that much more complicated. We can break down all the forces into weight force. That's the force applied by gravity. And that is mg acting down. And contact with outside objects somewhere along the boundary. Okay, so if you account for if you account for the weight and you account for all the places where there's contact, then you know you're done, you know. It's just a simple checklist you can go through to make sure that you're accounting for everything. And so first we, now starting to use Newton's second law, we use Newton's second law and what we know about motion and free fall to calculate the force that gravity applies to an object with a known mass. It's always mg acting down. Remember that example? We dealt with something in free fall. We know what its acceleration is. And there's something actually important to remember from that. And that is objects in free fall have the same acceleration, but different forces are applied by gravity, different weight forces. Okay, so at first that seems a little odd, you know, gravity's pulling harder on a bowling ball than it is on a pinball if you drop them from the top of, from the top of a roof or something. So gravity is pulling harder on the bowling ball, but the way Newton's second law works, they're accelerating exactly the same. Okay, it's pulling harder on the bowling ball, but it has to pull harder to make their accelerations be the same. So if you drop a bowling ball and a pinball from the top of a roof, they hit the ground at the exact same time. But the bowling ball makes a bigger dent in the ground because it has a lot more mass. It's a lot more resistant to being accelerated. So when the ground tries to accelerate it to a stop, it puts up a lot more of a fight, you know. And then, so we did that example of an object in free fall, and then we used what we learned about the weight, the force applied by gravity, to calculate the force that a scale applies to a person. standing at rest, and then to calculate the force that the scale applies to the person on an elevator that's accelerating, we did down, right? So now I'm going to do the same thing up, just sort of as a refresher about what we're doing. Notice that I think I didn't say this super clearly in this class. This is kind of the kind of interesting thing about this is like, how does the scale, so you use a scale to measure your weight, right? So how does the scale know your weight? I mean, the scale isn't you, so it's not applying, gravity isn't applying that force to the scale. So how does the scale get that information? Well, it gets that information exactly the way like we've been talking about it. Your weight pulls you down. The scale applies a force up to keep you from accelerating down into the floor. And it's that force between your feet and the scale that it's reading. It's not really reading your weight. And you saw that in the elevator example. Your weight doesn't change just because you're accelerating. You still have the same weight, but the scale reads a different number because it's not really your weight the scale's measuring, it's that contact force. Okay, so here's another example. Any questions about these examples before we do another one of these? Okay, so there's the elevator, scale, person, the person has a mass of 50 kilograms. So what force is applied to the person by the scale if the elevator accelerates upwards? I always do that. Elevator. Accelerates up at 3 meters per second squared. Okay, so Newton's second law says, we have to add up all the forces on the person. And so the first force on the person is the weight. That's 0, and then negative the mass of 50 times 9.81. And the only other force on the person is the force applied to the person by the scale. And these add up to be equal to the mass of the person times the acceleration. If the acceleration is 3 meters per second up, what's that as a vector? 0, 3. Yes. So we have 0, negative 490.5 plus F scale is equal to 0, 150. And we can break this up into two equations. With any of these vector equations, you can do that. So we have one that says 0 plus F scale's x component is equal to 0. And the second one says negative 490.5 plus F scale's y component is equal to positive 150. And so solve for this one, you get that F scale's x component is equal to 0. Solve for this one and you get F scale y component is equal to 640.5. So the final answer is the force vector applied to the person by the scale is 0x 640.5. And what are the units? Newtons, yep. And again, that's something you can, well, you could measure it on an elevator. I'm guessing elevators don't really ever get up to 3 meters per second squared. Maybe some do for acceleration. And also they don't stay at that acceleration. They accelerate to get up to their speed, and then they stay at a constant speed. So what you'd see if you stood on a scale when the elevator starts to go up is you'd see a little blip. You'd see your weight go up briefly, and then it would go back to your normal weight when the elevator stopped accelerating and just stayed at a constant velocity going up. And you can, feel that in your legs and everything. You have experience with that, the fact that briefly that contact force between you and the ground goes up. Yes. Any questions about that? Yep.
Okay, so in the first part of that equation, we have negative 50 times negative 1. Is that because the direction of motion is down and the elevator's going up? Is that why
No, this is always sort of a tricky thing. Like I think it's one of those kind of things that you for most people, you sort of won't make the distinction right, and then you will, but then you'll kind of go back and, it'll just take a while until it really is solid. But think of it this way, there are two totally different reasons that we use 9.81. They're both related to gravity, but they're two totally different things. One of those times is the one that we've done more often so far, and that is negative 9.81, 9.81 acting down is the acceleration that gravity causes in free fall only, So if an object isn't in free fall, then that's not the acceleration, right? And then the second time you use it is as a way to calculate the force that gravity applies, and that force is not the same thing as acceleration, and that force happens all the time, whether you're moving or not, and it's downward. So in this case, that 9.81 is turning up because that's the weight, that's the force that gravity applies to the person.
So when you're doing the force, it's positive?
No, it's always negative for both of them. That, the gravity's always applying a force down, and that force is making you accelerate down if nothing else is counteracting that.
So in that case, the 50 is positive?
Yeah, I guess you can think of it as the magnitude of the force is 50 times 9.81, and since the direction is down, I just made the whole thing negative then. Okay. Any other questions? So I'm sort of starting to set us up for maybe the second most important equation in this class, which is Newton's third law. Newton's first law sucks. I don't even talk about it. It's so stupid. No, it's actually Newton's first law is just, it's contained in Newton's second law. So it doesn't add any extra information. But as a setup, for Newton's third law, we need to talk about this, and it's just notation, but it's this notation that we're going to use a lot for forces. So force vector names. And I'm going to call this the subscript notation. Um, and so we'll refer to the force vector acting on body A by body B as FAB. Okay. So when we use this notation for force vectors with two subscripts like this, the first subscript is the thing that is feeling the force. It's the chosen object. And the second thing is what's applying that force. Okay. So FAB, in other words, is the force on A by B. Okay, so this is going to be a key thing in it. Notice that it's sort of, it's a little bit backwards from the way that we normally talk about things. We would tend to say the force B applies to A, you know? And so that's going to make it really easy for you to get these turned around backwards and think that FAB is talking about the force A applies to B. So get in the habit of thinking FAB is the force on A by B, on A by B, okay? The chosen body is that first one you're talking about, okay? Say it with me, on A by B. And keep saying it like that, and little by little say it more like you're getting hypnotized, like a zombie or something. So, on A by B, on A by B, on A by B, on A by B. Good. Okay. And so, yeah, keep that in mind when you're using that notation. I actually, as I was biking here this morning, I was like I fit this right into Mary Had a Little Lamb, and I was like, we could do it as a round tonight. But now I can't remember how it fit. It doesn't fit quite like that, so I don't know. Well, we'll do it later. I'll put it on YouTube or something, and you can do it in your room or. But it'll really help, that's for sure, singing it as a round. So in those elevator examples we just did, the force that I called F scale would be called the force on the person by the scale. Okay? On person by scale. I'm going to always say it like that too. And you might have a different, it doesn't matter what you call it as long as you know what each of these is referring to. You could call it force on passenger, that's still P, but you know what I mean. You could call it force on man by scale or whatever, but as long as you know what that letter refers to. One thing to notice about this, and it doesn't, I'll bring this up again because right now we haven't seen any examples where we deal with forces as scalars. So notice we'll eventually deal with some forces for which we know the direction. In that case, the variable representing the force will be a scalar. It won't be a vector, even though, and it's a little confusing right now to make sense out of it, but even though all forces are vectors, we'll sometimes represent forces by a scalar and a known direction. And when we do that, you can't use the subscript notation for those variables. Subscript notation is only for vectors. Okay, and later on when we get into this more, I'll give some examples to show why that'll give you backwards answers and stuff. But just remember that that subscript notation, you can only use that with vectors. That's right. That's right. You don't want to use that notation in that case.
No, but when you do F, A, B, you want to go over it? I don't know.
You do want to, yes. I did put it over, I hope. I think I did.
Oh, I see.
What's the repping force?
Representing. And the next thing we have to talk about is free body diagrams. I'm going to abbreviate these FBD. And by the way, people often call these full body diagrams. It's free body diagram. It doesn't really matter for your ability to do problems, but it makes you sound smarter if you use the right word. Not full body diagram. Somebody, one of my students once called it a free base diagram. It definitely is not that. Don't call it that. I can get into a lot of trouble. And these free body diagrams, they're like very specific engineering drawings that make it easier to use Newton's second law. They sort of organize your thoughts on what all the forces are. And so in this class, you must draw a free body diagram for each application of Newton's second law. So, I mean, I try to be flexible on a lot of stuff that, you know, if you have your own method from another class or whatever, most of the time I think I'm pretty happy to, deal with that. But with this, to me, this is really important. And so even if you get the right answer on a test, if you use Newton's second law and you don't have a free body diagram, you're going to lose a couple points, And, I think free body diagrams they're really important once you get to more complicated problems. For some of, like, as we're first talking about this stuff, all the problems are sort of simple. And so it's not, I don't think, super apparent why it's important to have one. It seems just sort of like an extra unnecessary step. But when stuff gets complicated, you'll be happy that you have like a sort of a set technique for doing this. Okay, so here are the steps for drawing a free body diagram. First, draw a closed outline of the chosen object. So in the elevator scale examples, that would be something like that, okay? There's no internal details on the person, and there's nothing else except the person. I didn't draw the scale or the floor or the elevator, okay? All there is just a closed outline. So not this, because that's not an outline, okay? You want to make this very clear what's the outer boundary of this thing. Or another example would be this, okay? That's a closed outline, but you have other things going on besides the outline, and also not the full drawing, okay? So don't do any of those. And the reason that the closed outline is helpful, we're going to use the free body diagram to show all the forces that are acting on a body. And remember, I said that in this class, the only forces are going to be the weight force and then forces acting on the outer boundary of the object. So the fact that you draw this closed outer boundary just makes it really clear to yourself where we're looking for forces. If you draw a stick figure like this, it's not as clear what's inside and what's outside. This, it's more clear. Okay, so that's the benefit of this. The second step is draw a downward arrow from the middle of the outline and label it with mg. If you know what that number is, you can put the number in. But label it with the mass times the acceleration of gravity. So for example, there's the outline. There's the arrow representing the weight force, and the weight force magnitude is 490.5. And notice that I didn't label it negative 490.5. Remember, multiplying a vector by a negative number switches its direction. So that really technically has the effect of being a double negative and saying that the vector is actually up with a magnitude of 490.5. So you just want to label it with a positive value. Okay. And then the last step, at each location, where an outside object contacts the boundary, in the first case, so there are two possibilities. You either know the direction of the force it's applying or you don't know it. Right now, we don't know the directions of any forces, so everything that we would do right now would fall into this first category. But if you don't know the direction of the force, draw a small coordinate system and label it using the subscript notation, that FAB notation. If, on the other hand, you do know the force direction, draw an arrow in that direction, and label it with a scalar value or variable. And this is the case where you don't use subscript notation. So in the elevator example, there's the outline, there's the weight, and then if you think about going around the boundary, the only place that an outside object touches the boundary is where the scale touches the feet. And so I drew the little coordinate system there and wrote F on the person by the scale. So that's a complete free body diagram for the examples that we just did. Any questions about that? Yep.
Okay, so if you were to draw the outline of a car,
Mhm.
would you have the two tires or would it be like a box? Because with the little stick figure, you would want two different like faces.
Yeah, I would. That wasn't the problem with it.
Oh,
It was just the fact that it needs to be like sort of a bubble with an inside and an outside. So, okay, yeah, thanks for bringing that up. So it wasn't, the issue here wasn't that it had 2 feet. It would be fine to do this. Okay. The issue is just that it has an inside and an outer boundary. That's the closed outline thing. So for a car, I usually, if you want to do it as a box, that's fine. I guess I usually do it as like a car. Don't make fun of my car. What if that really was what my car looked like and you really hurt my feelings deeply? Yeah. For now, that's okay. When we get, because right now, everything's particle stuff. So where things apply on the object doesn't matter. But later, it will matter, and then, but it'll be clear when we get to that point. So yes, squares or circles are okay with me, I guess. Although it's okay with me, but I think sometimes it does sort of help you clarify like where you're drawing your boundary, you know? But all right, let's do another example, another elevator example. So let's say that there's an elevator with a 5 kilogram box, and sitting on that is a 10 kilogram box. And on top of that is a 7 kilogram box. And let's say that the elevator accelerates up at 0.8 meters per second squared. What's the force vector applied? So I guess part A, what's the force vector applied to the 7 kilogram box by the 10 kilogram box? And part B, what's the force vector applied to the 10 kilogram box by the 5 kilogram box? And actually, let's do one more too. Let's calculate the force vector applied to the 10 kilogram box. Can we do this? 10 kilogram. Nope, we can't do this yet. So let's just do these first two. All right, so for part A, we're going to use Newton's second law to solve this, so we know we need a free body diagram. So I'll draw a free body diagram of the 7 kilogram box. So there's the object. There's weight acting on it. That's 7 times 9.81, 68.86. And the only place that an outside object is touching the boundary is down here, and that's the force vector applied to the 7 kilogram box by the 10. And I just did the comma because these have multiple digits just to keep it all straight. That's 7 times 9.81. Oh, yes, thanks. Six, 7. 6 times 9.81 is 58.86. I always get those. Anyways, you don't care. So Newton's second law says, so now sort of the benefit of this, and like I said, this is a simple case, so the benefit seems sort of marginal here, but the benefit is that every force that's on here goes over into the left side of Newton's second law. So it's just sort of a way of taking inventory. It's a picture that lets you chart out all the things you have to deal with. So we have one force here that's 0, negative 68.67.
So why don't you put the negative in the free body diagram?
Because the way to interpret this is you can think of it as it's a direction. You can think of that as a unit vector, a vector that has a length of 1 pointing down. So you can think of this thing as the vector 0, negative 1. And then you're multiplying it by this value. So if you multiply 0, negative 1 by negative 68.67, you get 0, positive 68.67. In other words, what that would mean is that the weight is acting up. Okay, so it's a double negative thing. You already have the direction from the direction of the arrow. You don't want to negate that, make it the opposite direction by putting a negative in there.
So we can just think of the arrow pointing down as the negative?
Right, yes. So 0, negative 68.67 plus F710 is equal to the mass, 7, times the acceleration. What's the acceleration vector? Yep, 0, positive 0.8. So we get 0, negative 68.67 plus F710 is equal to 0, 5.6. And that gives an x equation and a y equation. The x equation says 0 plus F710x is equal to 0. The y equation says negative 68.67 plus F710y is equal to 5.6. And if you put these together, you get a vector F710 is equal to 0, positive 74.27. And the units are newtons. Does it make sense that the 10 kilogram, that force applied to the 7 by the 10 is up? Because that's what this tells us, that it's an upward force. Does that make sense? Yeah, because if that 10 kilogram box wasn't there, the 7 kilogram box would fall, right? So the 10 kilogram box is, woo, woo, you know. Any questions about that? Okay, so now part B. We're trying to calculate the force vector on the 10 by the 5. And so if we're trying to calculate a force on the 10, your first thought is we want to isolate the 10 kilogram box. But the problem is we only have 2 equations. And if you isolate the 10 kilogram box, you're going to have a force vector that you don't know coming from the top and a force vector you don't know coming from the bottom. So that's a problem. You have too many variables. So instead of isolating the 10 kilogram box, I'm going to isolate the 7 and the 10 together, okay? And at first, that might seem a little weird, like, because those are 2 different objects. But if you remember that even things that we consider objects are really, you know, collections of molecules and atoms and stuff. There's really no such thing as something being an object and something not being an object. Anything you can draw a closed boundary around, you can do a free body diagram for. Okay. So I'm going to draw the closed boundary. The free body diagram is of the 7 and the 10. And so there's the outline. The weight is, well, the mass is 17. What's 17 times 9.81? Okay. And then where around the boundary is an outside body touching this? Only at the bottom. Yep. So there's a force vector here. Force, you can think of that as the force on the 10 by the 5. Or you could think of it as the force on the 17 by the 5, but they're the same thing. And what about the force here between the, like we just calculated this force between the 10 and the 7. What about those two? This is, in a way, this is, if this wasn't true, Newton's second law wouldn't be useful at all, because there's, if not infinitely many, at least billions of interactions between objects going on in any free body diagram you would draw, right? But the thing that makes it useful is we only are worried about the forces outside objects apply at the boundary. So any stuff going on inside the boundary doesn't have to appear in there, okay? And that saves us, like, maybe would make it impossible to solve for anything if that wasn't the case, okay? So this is a complete free body diagram. And I should say, you know, that's really why drawing the outline, the closed outline, is so important as opposed to a stick figure or whatever, because then you can be very clear to yourself about what are the internal forces that don't have to appear and what are the external forces that do. You know, that's what you're trying to do with this diagram. Newton's second law says 0, negative 166.77 plus F 10, 5 is equal to the mass, 17, times the acceleration, 0, positive 0.8. And the two equations that gives are 0 plus F 10, 5 x is equal to 0, and negative 166.77 plus 10 F 10, 5 y is equal to 0. And if you solve both of those for the two components, you get a vector F 10, 5 that's equal to, yeah, I wrote that wrong. Sorry. What's 17 times 0.8? So you get 0, and then 1, what is it, 180? Newtons. And on that one, does it make sense that the force on the 10 by the 5 is up? Yep, because it's the same thing, that the 5 is holding the 10 up. If the 5 wasn't there, the 10 would accelerate down. One little sort of nitpicky thing to notice here is that when you switch from talking about vectors to talking about the components of vectors, you don't use the vector symbol anymore because each individual component is just a number, you know? So F10.5 X component is 0. That's just a number, so it doesn't wear the hat. F10.5 Y is 180.37. That's just a number, so no hat, no fancy hat. Any questions about any of that? So next we're going to talk about the first type of force where we know the direction, where we're going to not treat it as an unknown force vector, but treat it as a scalar in a known direction, like a, okay. And that is cables and pulleys, and I'm going to write it just in parentheses so you remember that these assumptions are being made in these calculations. Weightless cables and frictionless weightless pulleys. Maybe you can imagine, like in some types of problems where the other forces besides friction and weight are huge compared to friction and weight. This will give good approximations. But if you have a problem where the other forces acting are small compared to the weight and the friction, then this will give really bad results. In engineering applications, if you're using cables and pulleys, you're usually using them to provide a lot of force, and so it gives a pretty good approximation in those cases. So let me say each cable has what's called a tension value that acts along its entire length. All a pulley does is change the direction of the force caused by that tension. And so here's how to calculate, here's how to do a free body diagram and calculate forces produced by cables. When a cable is attached to the chosen object, include a small stump of the cable in the free body diagram. then the force vector applied to the chosen object by the cable has a magnitude T. That T is for the tension. And it acts directly out of the stump. So let me do an example. So say that there's a hook hanging from the, attached to the ceiling, and hanging from the hook is a cable holding up a box. And the box has a mass of 10 kilograms. And we want to know what's the force vector the cable applies to first the block and second the hook. So a free body diagram of the block. So here's the closed outline of the block, and we're going to include just that little stump of cable in it. The cable force, the force applied by the cable, acts directly out of that stump with a value T. There's a weight force of 10 kilograms times 9.81, 98.1. Nothing else is touching around the boundary, so this is a complete free body diagram. Any questions about this? And then Newton's second law says, well, in components, what would this be? In vector components. A force with a magnitude of T acting in this direction. You do it the same way that we've calculated the components of our other vectors. It's just now we're going to call that T instead of a number. If you put the tail of the vector at the origin, you can see that, you know, you're trying to calculate the coordinates of this point. If the length of this vector is T, you just have the entire T acting in the positive Y direction. So that vector is just going to be 0T. Another way to think about it is the counterclockwise angle from the positive x-axis to the vector is 90 degrees. So you could do it as T times cosine of 90, T times sine of 90. Cosine of 90 is 0, sine of 90 is 1. So you end up, no matter which of those ways you do it, you end up with a value of 0T. Okay. And the weight force is 0, negative 98.1. And that's equal to the mass times the acceleration. It's just hanging there, so the acceleration is 0, 0. And notice that we're trying to calculate the force vector that the cable applies, right? When we solve an equation, we're going to find a value for this variable t, but that's not exactly what we want. What we really want is this force vector. This whole thing, 0t, is the force vector on the 10 by the cable. Okay, so once we calculate the value of t, we'll plug that value back in here. So say if t is equal to 50, then this vector is going to be 0, 50. So our two equations say, the first one says 0 equals 0. That's reassuring. Like if you forget what 0 is, that's like a handy reminder. And then the second one's even more helpful. T minus 98.1 is equal to 0. So that says that T is equal to 98.1. And then plug that back into the vector, and the force on the 10 by the cable is equal to 0, 98.1 newtons. Does that direction make sense? Yep, that force, it says that force vector is up, and you know that without the cable there, the block would fall down, so the cable has to hold it up, so that's right.
You actually lost in there with the t variables.
Mm-hmm.
Can you explain that again? Why we used 0 and t instead of like 0 and 1 for cosine of 90?
Yeah, well, we're talking about a vector that is in this direction and has a magnitude of t, okay? So like in the vector problems and stuff, our problems would always say it's in this direction, vertical, and has a magnitude of 50. And you do 50 cosine of 90, 50 sine of 90. Now, we don't know we don't know it's 50, we just know it's the variable t. But we do the calculation the same way. T times cosine of 90, t times sine of 90. And then once we figure out what t is, then we can plug it in here and get the vector. Okay. Any other questions? Well, we figured out what the force was that the cable applied to the box. The force on the box by the cable. On the box by the cable. On the box by the cable. On box by cable. So now we're going to figure out the force on the hook by the cable. And the key fact that we can use here is, so for part B, the tension T is the same all the way along the cable. So that cable tension that we calculated, 98.1, we can now use to figure out the force vector applied to the hook. Okay? So a free body diagram of the hook. So if we're talking about a standard A4 hook, and I don't know why you'd use anything else for a purpose like this. So what are the forces acting on the hook? Well, there's the weight. We don't know what that is. So sort of off to a bad start there. There is the force applied by the cable. That's the one we want. So I'll make a little stump of the cable, and it's acting that way. And this time we know the magnitude of that force. It's 98.1. Because of this fact, you know, in a single cable, the tension's the same everywhere. And now, is there anywhere else along the boundary that something outside is touching the object? Yes, exactly. Yep. So up here, there's a force. We don't know anything about it. We'll just call that the force on the hook by the ceiling. Okay. So there's a lot of stuff we don't know, but all we were asked for was the force on the hook by the cable, and that is this vector. Okay. So the fact that we don't know any of this other stuff, it ends up not causing us any problems. So the force on the hook by the cable, what would the angle be for this if you were going to use cosine and sine? It actually, you'd have to go all the way around to 270. You know, you have to put the tail of the vector at the origin of the coordinate system. So 270, and if you take 98.1 times cosine of 270 and 98.1 times sine of 270, you get negative 98.1 newtons. Another way you could do this is just eyeball it and say, I know that that's pointing in the negative y direction, and the magnitude is 98.1. This is 98.1 times the cosine of 270. Always, you know, cosine of the angle always gives you the x component, and 98.1 times the sine of 270 gives you the y component. Cosine of 270 is 0. Sine of 270 is -1, and so you get this vector. And does the direction of this force make sense? This says that the force is down. And you know, like if something you're hanging from a hook pulls the hook out of the ceiling, you know, it's pulling part of the ceiling down. You know that force is going down, right? So that makes sense. Okay. Any questions about any of that? Yep.
Where are you putting the origin of the coordinate system for, well, how are you getting to 70?
Well, remember, so this is stuff just right out of the vector problems. If you're trying to come up with the components of a vector, if you know this is your vector, the way you calculate those components is put the tail of the vector at the origin of the coordinate system and then calculate the angle. So there's the coordinate system. And so it's going counterclockwise from x. It's 90, 180, 270. And then 98.1 is the magnitude. Other questions? For a positive angle, you could also call this cosine and sine of -90, go clockwise, and it would give you the same thing. Yeah. Anything else? Okay, so next time we'll do this with pulleys. We'll see that really pulleys don't add much new, which is a little weird, I think, to some people. It was a little weird to me when I found that out, because maybe you've heard of, like, I don't know how many there are, but people talk about the simple machines. One's a lever, blah, blah, blah. I don't know what they all are, but one is a pulley. And you can use a pulley to lift, say, 100 pounds of load by applying, well, not one pulley, but you could rig up pulleys in a way where if you have 100 pounds of load, you can lift it up with, say, 10 pounds of force. So we'll talk about how to square the fact that a single pulley, all it does is change direction of force with this ability of pulleys to be rigged up to reduce the load.